Okay, so welcome to the final lecture in Module 2. So in this lecture, we are going to continue to talk about ensemble learning. So last time we discussed about random forest algorithms. So the forest the algorithm builds is an ensemble of decision trees trained with a method called bagging. So ensemble methods are machine learning methods that construct a set of predictive models and combine their outputs into a single prediction. So the purpose of combining several models together is to achieve a better predictive performance. And it has shown in a number of cases that ensembles can be more accurate than single models. And we can see an example here in this animation where the ensemble model predicts 8 of 10 correct, while model 1, 2, and 3 predicts 7 out of 10, 7 out of 10, and 6 out of 10. So for this to work, however, models included in the ensemble must not make the same kind of mistakes. So in other words, the models must be uncorrelated. So the intuition behind ensemble learning is often described with the phenomenon called the wisdom of the crowd, which means aggregated decisions made by a group of individuals are often better than the individual decisions. So many winning solutions in machine learning competitions on Kaggle are typically comprised of several ensemble methods. So today we will have a short recap of what bagging is and look at other popular ensemble methods, including bagging, or meaning boosting, where we are going to look at two methods called adaptive boosting and gradient boosting. And finally, a method called stacking. So let's start with looking into how to get diverse set of predictive models. So ensemble methods work best when the predictors are independent from one another as possible, as I mentioned earlier. So one way to get diverse classifiers is to train them using different algorithms, as we can see here with logistic regression, support vector classifier, random forest classifier, and others. So let's say you have trained a few classifiers on a certain task where each one is achieving around 80% accuracy. So a simple way to create an even better classifier is to aggregate the predictions of each classifier and predict the class that gets the most votes. That's what we are doing here. So this is called hard voting and is also known as majority voting. So how do we do this in Scikit-Learn? So here's an example from the book. So the following code creates and trains a voting classifier composed of three diverse classifiers. So you have so you can see here that we import random forest classifier, voting classifier, support vector classifier, and logistic regression. So yeah, and we define them here, and we define the voting classifier here with the three classifiers. And we define here that we want to do hard voting. And in this piece of code, we train each of them on the training set and predict on the test. And here are the accuracy for each of these models on test set. And you can see that the voting classifier achieves slightly better results than the three other models, each one for themselves. So there is also another way to do voting. So if all classifiers are able to estimate class probabilities, as we can see here with class 190 for classifier 1, while classifier 2 says 10, and so on. So then one can use this to predict the class with the highest class probability, average over all individual classifiers. So this is called soft voting. It often achieves higher performance than hard voting because it gives more weight to highly confident votes. As you can see here, it classifies it to class 2. And in Scikit-Learn, you just write soft instead of voting, but then you have to look into if the model you are using has support for it. It should have a variable called estimate to do this. Okay, so another approach to get a diverse set of classifiers is to use the same training algorithm with a technique called bagging, as we discussed in the previous lecture with random forest. Okay, so let's look at how bagging works. So you have multiple subsets that are created from the original data with replacement. So with that, I'm meaning that individual data points can be chosen more than once. So you can see that here with the red points here. So we have only 5 red points here, while in one of the subsets you have more than that. So which means that some of the data points are chosen more than once. Okay, so the next step is to train a model on each of these subsets. And you can train them in parallel with different CPU cores or even different servers. So finally, you predict on new instances by aggregating. So you have an ensemble classifier. Yeah, so you make predictions based on that. So now let's look at another ensemble technique called boosting. So boosting attempts to build a stronger learner, so a model that achieves high accuracy from a number of weak learners. So models that perform slightly better than random guessing. So the general idea of boosting is to train weak learners sequentially, each trying to compensate the errors made by the earlier ones. So there are many boosting methods available, and today we will look at 2 popular boosting methods called AdaBoost and gradient boosting. So AdaBoost is short for adaptive boosting. AdaBoost combines the predictions from short 1-level decision trees called decision stumps. So it puts more weight on difficult to classify instances and less on those already handled well. So let's look at how it works. So we started with all points start with equal weights. The training algorithm involves starting with a 1-level decision tree and finding those examples in the training data set that were misclassified. So you can see here, these are correctly classified and these are correctly classified, but these are misclassified. So we want to add more weights to those examples. So another tree is trained on the same data, although now weighted by the misclassification errors, as you can see here. So these are more weighted from previous iteration. So again, misclassified training data have their weights boosted, and the procedure is repeated until a desired number of trees are added. So finally, you can see that we can classify all of them correctly. Okay, so next, let's look at gradient boosting. So gradient boosting is a method that goes through cycles to iteratively add models into an ensemble. So the objective here is to minimize the loss function of the model by adding weak learners using gradient descent. So the idea is to start with a naive model and make predictions. These predictions are used to calculate a loss function like root mean squared error. So the next step when training a new model, gradient descent, is used to decide the model's parameters, so that adding this new model to the ensemble will reduce the loss. So finally, we add the new model to the ensemble. Then we repeat this process until one reaches a stopping criteria. So instead of this module, I mentioned that XGBoost is state-of-the-art model used on tabular data, emphasized by this paper from 2021 that shows that XGBoost outperform deep learning models. So this is the model that dominates many tabular data competitions on Kaggle, as some of you have noticed. So it is a specific implementation of the gradient boosting method, which uses more accurate approximations to find the best tree model. So it employs a number of nifty tricks that is exceptionally successful, particularly with structured data. So pointed out here. So an interesting thing here is that in this paper, they outline that the positive side is that they show that an ensemble of deep models and XGBoost performs better on these data than XGBoost alone. So now you understand what this means. Okay, so the last ensemble method we will discuss in this lecture is called stacking, short for stacked generalization. So you train a model to aggregate the predictions of all predictors in an ensemble instead of using trivial functions like hard voting or soft voting. So here you have each of three predictors predicts different values, so 3.1, 2.7, and 2.9. And then we have a final model called a blender or a meta-learner that takes these predictions as input and makes a final prediction, which is 3 here in this case. So how do we do this? So a common approach is to use the holdout set. So first, the training set is split into 2 subsets, as we can see here, subset 1 and subset 2. The first subset is used to train the predictors, as we can see here, and subset 2 is still holdout. Okay, so now we have trained predictors on subset 1. These predictors are then used to make predictions on the second subset, as you can see here. This ensures that predictions are clean, since predictors never saw these instances during training. Then we can create a new training set using the predicted values as input features and keeping the true value. So the blender is trained on this new training set, so it learns to predict the target value. So that's it about ensemble models. So I know that some of you are still a bit confused of this train test split. I know this could be very confusing in the beginning. It's important to do a couple of iterations in the process of applying machine learning. So, okay, so I will just have a quick recap of the idea with train test split, and I hope it makes it a bit more understandable. Okay, so we have 2 different methods. So we start off with this holdout method for training machine learning models. So we have this entire data set. So this could be the house pricing data set in this assignment 1. And then you commonly split this data into 80-20 with training and test. So I have made this split for you in assignment 1. So you don't need to worry about this now, and you don't have any labels on the test set as you have as you should have notified. So your task is to split the data, your training data that you have available, as the CSV file says as well. It's training.csv. So split it into like 10 to 20% of training set. So you should split them based on some criteria to get a better estimate. So that's called, yeah, like with stratifying it. So I will come back to this word stratify. So when you have done this and got an estimate and are happy with tuning your model, then you train your final model on the entire training set and then predict on the test set. So another approach to this is, okay, so this is done by me, where you have the test set. Then with the training set, you can use cross-validation instead of doing this holdout set. So you partition the data into k equal size subsets. So you train your model on each of these subsets as shown by this animation, to calculate the average error across all k trials. So finally, when you're happy with your tuning of model, then you train on the entire training set. So you use the whole set before you predict on the test set. Okay, so you will do this train test split yourself in assignment 2, and then it's important to not touch this data until you have fine-tuned your model to get an unbiased evaluation. So when you do it here in assignment 1, it's first of all for that you are getting like an introduction to how thing works. And in Kaggle, the test set is split into 2, as I mentioned on Discord. So you have a public data set and a test and a private test set that will be evaluated at the end of the assignment to see how we perform on the final test set. So this could vary from the public data set. So you shouldn't tune your model towards the public test set. Okay. So let's assume you are doing a multi-class classification and have an imbalanced data set that has different classes, as shown here with skin lesion classes. So you have several classes here. So if you do a simple train test split that does a random split, totally disregarding the distribution of or proportions of the classes, what happens in this scenario is that you end up with a train and a test set with totally different data distribution. And some of you have experienced this in assignment 1, where you have made this holdout split. And when predicting on the test set on Kaggle, you get a different performance score. So therefore, you may want to use stratification to ensure the same distribution of classes is in both sets. So in Scikit-Learn's documentation for train test split, you have a parameter called stratify. So data is split in a stratified fashion if it's defined using the class label, so the Y label. Okay, so finally, I know some of you say that it is not easy to get like overview of all these steps by going through the book. So the authors of this hands-on machine learning with Scikit-Learn and TensorFlow, they do have a GitHub repo, and in their GitHub repo, they have a notebook for chapter 2 end-to-end machine learning project, where they go through all these steps in one notebook. So it's easier to get an overview here, but yeah, use this as an inspiration and don't copy everything. And in the assignment, you should explain what you are doing through the entire notebook. And with that, I'm thinking that we are done now. So I will be available on Discord during the lecture hours. Okay.